ESS Ecosystems and Ecology 1 Part 2 examines productivity as the transformation of energy and matter into biomass. Productivity values are rates presented in energy or mass units over time. The significant ideas are the interaction of species with their environment result in energy and nutrient flows. Ecosystems are linked together by energy and matter flows. The sun's energy drives these flows, and humans are impacting the flows of energy and matter both locally and globally. And lastly, photosynthesis and respiration play a significant role in the flow of energy through communities. Here's an outline of the ecosystems and ecology units. There are two distinct units, Ecosystems and Ecology 1, Ecosystems and Ecology 2. This movie is focused right here. I've come back to this IB syllabus statement just to strengthen it. Distinguish between the biotic and abiotic components of an ecosystem. The biotic factors in an ecosystem include predation, herbivory, parasitism, mutualism, disease, and competition. Remember that most of these terms will be covered in the next unit, Ecosystems and Ecology 2. The physical factors, the abiotic factors, include temperature, sunlight, pH, salinity, and precipitation, rainfall. An ecosystem would be the community, the different species, and the abiotic factors, the chemical physical factors, interacting together in a given location. In this photograph, the ecosystem includes the plants and animals of the desert interacting with each other as animals feed on plants or animals feed on animals. The ecosystem would include rattlesnake eating rats, this is predation, or rats eating grasses, this is herbivory. And the ecosystem includes the plants and animals of the desert interacting with the abiotic environment, adapting to the abiotic environment, adapting to the lack of rainfall, the high and low temperatures. These are abiotic factors typical of a desert. In this diagram, you can see two food chains, and each chain exists in a community, which is a group of different species living and interacting with each other in a common habitat. Food chains display feeding relationships. The trophic level is a position that an organism occupies in a food chain. Organisms that photosynthesize are producers. Producers are plants or algae, phytoplankton, that produce their own food using photosynthesis, and they form the first trophic level in a food chain. Now with this slide, I can introduce the term productivity, which is a transformation of energy and matter into biomass over time. Photosynthesis transforms energy and matter into biomass over time, and feeding ultimately results in the transformation of energy and matter into biomass of consumer populations over time. Gross productivity is defined as the total gain in energy or biomass trapped in organic matter per unit area per unit time, either through photosynthesis, which is the primary producers, or by assimilation in consumers. Just keep your eye out for the distinction between feeding and the word assimilation. So here's our first IB syllabus statement of this movie. We'll keep it simple to start with. Define the terms gross productivity, net productivity. So the gross productivity of producers would be the total transformation of light energy into chemical energy, the transformation of light energy and matter into the biomass of plants. The gross productivity of consumers would be the total transformation of energy and matter in food into the biomass of the consumer. Now, net productivity is the gain in energy or biomass per unit area per unit time remaining after organisms use some of the energy for their own needs. In other words, after respiratory losses. And respiration releases heat to the universe, increasing the entropy of the system. So with this slide, I would like to dig deeper into these productivity terms. Please pay close attention. I've already asked you to define gross productivity and net productivity. Primary productivity refers to producers, photosynthesizers only. Secondary productivity refers to consumers, consumers at any trophic level, primary consumers, secondary consumers, consumers only. And then, from given values, calculate net primary production, gross secondary production, net secondary production. I will introduce these calculations in this movie, and I'll strengthen them in part 4. Here is a model of a plant system, a producer. At the top of the slide, I have defined gross primary production, GPP, as the total gain in energy or biomass per unit area, per unit time, it's a flow, fixed through photosynthesis. Producers, plants, transform solar energy and matter into the biomass of plant organic matter per unit time. Once the producers transform solar energy and matter into the biomass of the plant, they will use some of this chemical energy for their own needs. In other words, they respirate. The amount of biomass left over after respiration is called net primary production, NPP. It's defined as the gain by producers in energy or biomass per unit area, per unit time, remaining after respiratory losses. Organisms use energy to maintain their own order. The organization of an organism, the complexity of an organism, the high order of an organism is maintained by the transformation of energy, and in so doing, heat is released to the universe, increasing the entropy of the system. In this diagram, we see a plant growing over time. The rate of photosynthesis, carbon dioxide in, would have to be greater than the rate of carbon dioxide out, respiration. The plant increases its mass because its inputs are greater than its outputs. Total photosynthetic transformation of energy and matter is GPP, gross primary productivity, the input. Total respiration, the energy used with the release of CO2 for the plant's own needs, is the output. GPP minus respiration is net primary productivity, the amount of biomass left over after respiratory losses. If GPP is greater than respiration, then NPP is positive and the plant grows in mass. NPP is equivalent to the new mass of the organism, the new mass gained over time. Hopefully by this point you have some grasp of gross productivity, gross primary productivity, and net primary productivity. I have yet to be specific about secondary productivity. That's coming up. While we've done no calculations up to this point, you might be able to see the mathematics in calculating net productivity. In other words, gross productivity minus respiration results in net productivity. So net primary production is the gain by producers in energy or biomass per unit area per unit time remaining after respiratory losses. It's important to emphasize that production occurs over time. Its measured rate units typically are per year, and this diagram displays why we measure productivity over a year. In the warm season, net primary productivity is positive as total photosynthesis, GPP, is greater than respiration. If the tree adds biomass, NPP is positive. But in the cold season, or low light season, respiration is greater than GPP, so NPP might be 0 or negative. But over the entire year, the tree increases its biomass, the tree grows. Thus, GPP over the year is greater than respiration over the year. NPP is positive over the year. The growth of the tree over the year, or many years, is the NPP, and that's the new mass over time. Now, if humans harvest the tree after a certain period of time, this is a yield. Humans harvest the growth. Humans harvest NPP. NPP is the equivalent to sustainable yield. The yield is sustainable as long as a new tree is planted for every tree harvested. This diagram should look familiar to you as a system in steady state equilibrium with gentle oscillations over time. The graph displays the mass of a forest ecosystem over time. The forest is photosynthesizing and respiring at the same time. Thus, the growth seen here represents net primary productivity. Each increase in mass represents positive NPP, values which could be determined from the y-axis. Now, humans impact the system by harvesting at the end of a time period to return the system to an original mass. Humans harvest the NPP. Again, the magnitude of the harvest can be determined using values from the y-axis, and the process repeats itself. Humans have a sustainable yield in harvesting NPP and allowing the system to regrow in each time period. Now let's move on to look at secondary production, the production by consumers, animals particularly. What you see here is an animal with a mouth into which food goes, but what consumers put into their mouth is not exactly what they take into their body, because some of what they eat goes out as feces. Thus, we must think carefully about secondary production. Please pay close attention here. Secondary production is the amount of energy that enters the bloodstream of the animal, this flow here. This flow is known as assimilation, and it's food eaten minus feces. So here's the definition. Gross secondary production. Gross secondary production is the total gain of energy or biomass by consumers per unit area, per unit time through assimilation. In other words, gross secondary production is food eaten minus feces. You can see all of this in the diagram. Food ingested, passed along the digestive tract, some of what's eaten goes out of the body as feces. However, some of what's ingested goes into the bloodstream, into the body. This is the energy and matter assimilated by the consumer. This is gross secondary production. Then the consumer uses some of the assimilated energy and then respirates that with a release of CO2. And we have net secondary production, which is GSP minus respiration. Net secondary production is the new change in mass of the animal over time. So once again, secondary production refers to consumers at any trophic level. Gross secondary production is food eaten minus feces. This is the energy and matter assimilated, represented by this flow here, into the body of the organism. Net secondary production is gross secondary production minus respiration, or food eaten minus feces minus respiration. Net secondary production could also be defined as a change in the mass of the consumer. Net secondary production is the biomass remaining after respiratory losses have been subtracted from gross secondary production. One more example. If I feed and poop and respirate exercise over a 24-hour period, and I find that my mass to have increased by 1 gram over that 24 hours, my net secondary productivity is 1 gram, the change in the mass over 24 hours. Using this image of a lion feeding on a zebra, remember that feeding is not gross secondary production. Not all of what consumers ingest ends up in their bloodstream for metabolism. Some of the ingested food passes out in the feces. So gross secondary production is the total gain of energy or biomass by consumers per unit area, per unit time through assimilation. Gross secondary production is food eaten minus feces. Then once the consumers have taken up the energy and matter from the environment, this is the input, in other words, this is GSP, they use some for themselves by respiring, that's the output. Respiration provides the energy for movement, among other cellular activities. So net secondary production is the gain by consumers of energy or biomass per unit area per time remaining after respiratory losses. Net secondary production is food eaten minus feces minus respiration, or net secondary production is GSP minus respiration. Another way to think of net secondary production is the new mass over time. As a last note, if GSP is greater than respiration, then the consumer gains mass. If respiration is greater than GSP, then the consumer loses mass. Here's your first opportunity to calculate values of productivity. Using the diagram, can you calculate gross secondary production? and net secondary production over a time period of 30 days. Now you can turn the movie off now or follow along with me. Now GSP would be calculated as food eaten, 200 joules per 30 days, minus feces, 100 joules per 30 days. So GSP would be 100 joules per 30 days. Now, net secondary production is GSP minus respiration. Respiration is seen here as 67 joules per the 30 days. So if GSP is 100 joules per 30 days, respiration is 67, then net secondary production is 33 joules per 30 days. Notice the rate unit. Productivity is a flow, and as a flow, it has rate units. Using this diagram, could you write equations for GSP and NSP? Now, GSP is food eaten minus feces. GSP is this flow. GSP is A for assimilation. Now, NSP is GSP after respiratory losses have been subtracted out. All organisms respire to provide energy for movement or active transport of materials across cell membranes or building molecules. So NSP can be seen here as A minus R. Keep in mind all productivity units would be measured as rates. Here's a graph showing the change in mass over time of a cattle farm with the added output of humans taking a harvest at the end of each year. Through this time period, the cattle are eating, pooping, and respiring, so the increase in mass over the year represents net secondary production. Calculate the net secondary production of this farm using the y-axis. The net secondary production, this growth, is 10 times 10 to the 6 kg per year. As a note, we do not know how much the cattle ate, nor do we know how much feces they produced, and we're not given any information about how much they respired. Thus, we cannot calculate GSP from the information given here. All we can see is their net change in mass over time. So as we start to bring this movie to a close, let's do a little review. We're looking at incoming solar energy to a leaf with the leaf cell seen right here in green as energy arrives to this system, in this case the plant. Some is immediately reflected, some serves to evaporate water, and some is transformed by the plant by photosynthesis, and this transformation is gross primary production. Remember now that I'm using the term primary as a reference to producers, plants. Now the plant uses some of the energy for its own needs. This would be respiration, and it leaves behind some biomass known as net primary production. This is the energy or biomass left after respiratory losses have been accounted for. Now there's another way to understand net production. If you're thinking about food chains, net production is the energy available to the next trophic level up. In this case, as we look at a plant, NPP is the energy available to the primary consumers. So at this point, you should have a reasonable understanding of these IB syllabus statements. From given values, calculate net primary production, gross secondary production, net secondary production. State that maximum sustainable yields are equivalent to the net primary or secondary productivity of a system. I will strengthen the calculation of values in Part 4. In this diagram of a plant system, we can see the inputs of energy and matter in the process of photosynthesis resulting in GPP. The plant community then respires, and that's an output, and the difference between GPP and respiration is NPP. And over the time period, year 1 to year 2, the community increases in biomass. So GPP as an input is greater than respiration as an output. The community has a positive NPP, and we can see that as an increase in biomass over the course of the year. Now, NPP could be calculated by subtracting the mass of the community year 1 from the mass of the community year 2. The net primary productivity value is also called sustainable yield. Now this graph displays the growth of a bean plant over 22 weeks, and I'm asking you to describe the balance of photosynthesis and respiration at different times. The bean plant is photosynthesizing and respiring during the entire time period, so what we're looking at here is simple growth, in other words, net primary production. The plant is growing, so GPP is greater than respiration, but that's all we know about GPP or respiration. We cannot calculate values for either GPP or respiration from the information given here. NPP during the 8 to 12 week time period is approximately 30 grams over the 4 weeks, or 7 to 8 grams per week. Now after week 18, the plant begins to decline in mass. In other words, respiration is greater than GPP through this time period as the plant begins to die. It's an annual plant and dies soon after one season has come to an end. And that brings us to the end of IB ESS Ecosystems and Ecology 1, Part 2.